Hi everyone, this is our notes on the scientific method. So what is the scientific method? It is the method that is used to explore observations and solve problems. I hope sometime even in elementary school or last year, you've heard of this word before. It's pretty much the steps that scientists use in order to learn something new or discover something. Right here we have this very important word, hypothesis. It is a explanation for a proposed phenomenon. So this is kind of like they always call it your educated guess, right? It says educated because we are taking things into account um, while kind of guessing what just happened. So let me give you an example. So you don't have to write this, but here's our scenario. You come home one day and find that your iPhone charger has been cut in half and you see bite marks on it. What do you assume happened? So even in a simple situation like this, you are actually using the scientific method. So give it a second, think about it. What do you assume happened given that scenario? So hopefully you would have said something like, my pet did it, right? If you have a pet, that is likely the answer that you're looking for or the hypothesis that you would make. If you don't have a pet, then it becomes a little bit more complicated than that, right? So that right there, just starting with that kind of train of thought, you're actually creating a hypothesis. So here is our scientific method flowchart. This is the steps that scientists or even us, we're going to be using this in order to create our experiments and learn about certain things. So the first one is observation. So if we're going to continue to use the iPhone scenario as our example, right? So you come home, you see your charger, it's broken, it's chewed up. That is an observation. You're looking at something, you see something, you smell something, right? You feel something. That is an observation. From there, hopefully you would ask the question, what the heck happened to my charger? Right? Or why is my charger all bitten up? That is the question that comes from our observation. And then you create the hypothesis. Again, assuming you have a pet, you're going to say something like, my cat or my dog or my rabbit, right, bit or chewed up my cord. That is my hypothesis. And then you are going to conduct an experiment. This one, nothing too scientific about the experiment, but you're going to maybe see, okay, does this bite mark match more of my dog? Or does this bite mark seem more something like my cat would do, right? Or is this bite mark something that my baby brother would do? Hopefully not, but that kind of an experiment because we're looking more at qualitative data, which means that it's more of an observational one instead of like measuring and stuff like that. And then you uh, analyze your data, right? Maybe you'd say, okay, well, this was here, my pet was there, blah, blah, blah. So all that brainstorming that you're doing, you're analyzing what you see in the room, you're analyzing what it is that you can see in your surroundings and what you know of your pet or something else. Again, if there's no pet and you see bite marks on your charger, then I mean, a logical explanation might just be this is not my charger, or something came in here, maybe like a rat or a mouse that came and chewed up my charger. And then conclusion, right? So maybe, your cat, your dog looks kind of guilty, and so you conclude that, hey, my pet did chew up my cord, right? But then it doesn't end there. You report it out. And usually, I don't know about you guys, but if somebody chewed up my charger, right, I tell my husband, I tell my siblings if they're around, right, and I say, hey, my cat chewed up my charger. You report out, you share your findings to the scientific community, or you share your findings with your friends, right? And technically, it doesn't actually stop there. You can go back to question, or you can go back to hypothesis, right? And you can come up with a new question and say, why is my charger even in the living room? I put it in the bedroom, something like that, right? Or why is this chewed up when my dog is in the backyard? You come back and ask another question. What I would ask you guys to notice here are these arrows. Whoops, zoomed in too much. These arrows right here. See how they're double-sided? right? Because you can go back and forth. There are some studies where they never get past hypothesis, right? Or maybe they never get past experiment. They have to keep going back and making a new hypothesis, make a new hypothesis, and never actually conclude something, right? That is totally possible. So this is a free-flowing method, right? Just because you stop that report out doesn't mean you're done, right? If your research has more to offer, then you keep doing it and you keep expanding. That's how we learn new things, right? But this is just the general structure. Okay, so in every experiment, we have three types of variables. We have the independent variable, or the IDV, that's just a shortcut for it, which is the variable being changed. We have the dependent variable, which is the one that's being measured, and then the controlled variable, that is the one that stays the same. So whenever we do experiments, you're going to want to have to just explore one variable, right? Because if you have multiple things going on at the same time, it makes your experiment inaccurate and it makes it harder to really pinpoint what it is that is causing your experiment to turn out that way, right? So independent, dependent, and then control variable. So let's take a look at this scenario. It says, here's a question: which chocolate bar has the most calories? So doesn't sound like an experiment, but it is. It's an explorative experiment. So let's say you have, I don't know, you have a Hershey's bar, you have a Snickers bar, whoops, Snickers bar. Let's see, what else we got? Reese's is not really a bar, but I can't think of anything else. So we have those, and this is probably not true, but let's just say this is 100 calories, this is 150 calories, and this is, I don't know, 75 calories. Totally not accurate there. So we have to figure out what is our independent, our dependent, and our control, right? So let's look at our definitions again. I'm sorry. Let's look at our definitions again. So independent variable is the variable being changed. So what is changing here, right? What is changing? Your two choices are the chocolate bars or the calories. Hopefully you said the chocolate bar, because those are what we are exploring. We're trying to see which chocolate bar has the most calories, right? So what we're going to do if we're actually doing this experiment is we would get a whole bunch of chocolate bars and then look at the nutritional value and compare. So then going back to dependent, so dependent is the one being measured. So what are we measuring? We are measuring calories, right? And again, this one, it's more of looking at numbers. There will be times where we are actually measuring, temperature, mass, volume, even time, stuff like that. So that is our dependent. And then control, something that should stay the same, right? So if I was conducting this experiment, what would make my caloric count as accurate as possible? Think about it. Okay, hopefully you said the size of the bar, right? There's usually size of the bar. So there's usually a lot of controlled variables, and again, you want it as controlled as possible to make sure that the variable that you're changing is the same. So what I mean by that is you're not going to get a Hershey bar that's this big, and a Snickers that's this big, and then a Reese's that's this big, right? That is not accurate, because obviously the bigger an ice cream, the bigger a chocolate bar is, right? The more calories it's gonna have, and then you might be giving false information by saying, well, the Snickers is the one that has the least calories because it's small, right? But if you look at the numbers and you're like, oh my gosh, 150 calories for that tiny thing, that's not healthy. So what you would want is you would want, pieces or the mass of your chocolate bar to all be the same, right? So we're gonna, do a lot more practice with that. But that is something important that you need to know when setting up experiments. So graphing, we're gonna do a lot of graphing. The good part with you guys is that this can be done on the computer, but I still need you guys to do it on paper. So we're gonna practice both. So why even use a graph, right? So a graph can help create a visual for people, makes it easier to look at trends and patterns, right? I don't know about you guys, I'm not really a numbers person. If you're a numbers person, you can see the trends really quickly. But for visual people like myself, you can take a look at a trend a lot easier when you're looking at a picture. So like if we take a look at this diagram down here, right? We can see that the graph is trending upward because you can see, if you plot all those points, it's trending upward. Again, you can see that with numbers, but a lot of times, especially now for me, like I've mentioned to you guys, I'm taking my master's. One of the little quick tricks that I've learned reading all these scientific papers is to look at the graphs, right? Because it summarizes the data really quickly without me having to read through, pages and pages of results and analysis. Okay, we got raw data. So when you do an experiment, you collect something that's called raw data. So this is just something that has not been analyzed yet, right? So once we're doing an experiment and you're, writing down all the numbers, all the measurements, right? That is called raw data. And then you have to put it in an organized data table like this one, right? So it's organized, it's raw, it hasn't been analyzed yet, but we can see kind of a trend, right? This is like the step you do before you create a graph, right? You have this is called a figure title. We're gonna practice doing that and making papers and stuff. And then you're just gonna make your raw data into a nice little table like this one, right? So we have different types of graphs. We got bar graph, line graph, pie chart, scatter plot, and pictograph. Most of the ones we're probably going to use is bar graph and line graph, maybe sometimes pie chart. These ones, not too much. Doesn't mean we're never going to use them, but just in this class, that one's kind of hard to use, but we're going to focus on the top three. So bar graph. How do I know when to use this? You use a bar graph when you are comparing data from similar groups, right? And this is better used when comparing large changes. So here's a example graph for you, right? It's titled nicest fruit. We got different kinds of fruits on the x-axis. This is the x-axis right here. This is our y-axis, right? And when we start talking about lab reports, we're gonna practice how to write these graphs properly. But anyway, let's take a look at the graph. So this one looks like it was a survey. I know that because it says number of people, right? So they probably took a survey asking how many of them think either one of these fruits are the best fruit, right? And just by looking at that graph, you should be able to tell me that the blueberry is the one that is the nicest fruit according to 40 people, right? And then hopefully you can also tell me that grapes, unfortunately, seems to be the one that people think is not the nicest fruit, right? But I can see that very quickly with a picture. You can also see that very quickly with a number. A lot nicer to look at when it's a picture, right? But you are comparing data because all of these are fruits, right? So you're comparing which fruit is the best. That is when you use a bar graph. Okay, so here is a practice. Going back to IDV and DV, right? Remember IDV is the one that's changing and DV is the one that's being measured. So take a quick second, pause it if you need to. Using this scenario, what are our variables? Okay, so hopefully you said that the fruits are the ones that's changing and the one that are being measured is the number of people. Let me give you guys a little trick here, right? Your IDV, your independent variable, it's always going to be your x-axis. And your measured variable, your dependent, will always be your y-axis, right? And I have a funny little mnemonic for that. It's kind of silly, but it's just something that I used to help me remember it. But independent variable, I remember that this is the x-axis because when I break up with someone, I'm independent from my ex-girlfriend, ex-boyfriend, right? And then dependent is the y. Why should you be dependent on your ex, boyfriend or girlfriend? It's silly. If that doesn't help you, don't worry. But you're going to see more of those funny mnemonics along the way. Okay, moving on. Okay, line graph. Line graph is used usually when you're tracking change over time, right? And then this is better looked at when you're tracking small changes. And again, this is just in general, right? You can use a bar graph when it's appropriate. You can use a line graph when it's appropriate. You just got to think about what's best. So let's take a look at this example, tree height in feet. If you wrote this lab report, you would lose points because you are missing important labels, right? Like down here, your x-axis. What is that? I don't know what that is. Is that, number of Dalmatians or number of trees? I don't know, right? But we can extrapolate or assume that this is probably looks like it's years, right? And then this one, it's tree height in feet. So whenever you guys make a graph, make sure that you label it, make sure you have a title, make sure you have a legend, and make sure you have your axis labels, right? So we are tracking change over time. We're trying to see how much the tree has grown every year, right? And we see that it's growing because the height of the tree is increasing. Hopefully that one is a little bit easier to see. So again, tracking change over time. Okay, so here's a pie chart. This is a visual that is usually used to compare percentages. So you can see here, the pie is the whole, right? So if you have, like this example right here, if the lunch sales, this is everything that the cafeteria sells, and they want to know, how much of each is getting sold, then they make a pie chart, right? So you're comparing pieces and a whole. That one's a little bit easier and a lot easier to make as well. So like I said before, different graphs can be used to show different types of data. Just think of what would be most suitable to show your purpose. Okay, practice with metric. This one involves a little bit of numbers, involves a little bit of practice. So if you need to make sure that you go back and watch it again, practice on your own. I'm going to give you practice questions on these as well. So what is a metric system? Right, a metric system is the system of measurement that is internationally agreed upon. So every country uses this kind of measurement, except us, USA. We do not use it. So see, it's internationally agreed upon, and every country uses it except for us, unfortunately, right? And if you've ever traveled to another country, you might have noticed something like the roads and the freeways, right? A lot of them use kilometers or meters. What do we use for ours? Yeah, we use miles, right? That's different. Those do not interchange. Just because I said 1 kilometer, that does not equal 1 mile, right? So let me tell you a little backstory. I used to have a hamster. His name was Gene. And when I was making his cage, I was watching a video from someone from England, from the UK, right? And all her measurements were in centimeters and meters, right? So I wrote it down because that's all the measurements that I have. And then I went to Home Depot looking for some wood. And I told the guy, here are the measurements that I need. And then he looked at me and he's like, could you put those in inches? Because inches are what we use, right? So when I go and I, converted it, I asked help from Google to convert it. But when I go to put the lid on the cage, it didn't fit exactly because of the discrepancy, the gap between the metrics and our American system. It's not exact. So there was a little bit of a miscommunication on there. So just a little fun tidbit for you. So things we need to measure. And we'll measure a lot of these, maybe not all of them, but most of them. So we have mass, which is how much matter or atoms an object is made out of, and weight, a measure of the force of the gravity. So if you take a look at it, mass on this picture is measured in kilograms, right? And then weight is measured in newtons, N, like Isaac Newton, newtons. So when you go and weigh yourself on a weighing scale, what is the unit that it shows you? Hopefully you say pounds, right? It's usually like lb, pounds, right? So the difference between mass and weight is that mass stays the same. So if you look at the moon and the earth, this person on the moon um, has a mass of 120, and on earth has a mass of 120, because when you go from the earth to the moon, right, the number of atoms that you have, it doesn't change. You're still the same mass, right? You're still the same amount of atoms, but the weight changes. So take a look at this. It's 1,200 newtons on Earth and then 200 on the moon, right? Because the weight is related to the gravity of the Earth. So gravity is, I'm sorry, weight is pretty much how much the gravity is pulling you down. That's the definition of weight, right? So if you want to lose 1,000 newtons, then go ahead and go to the moon. Go to the moon, because the Earth's gravity does not work as well on the moon. It doesn't pull as much. You have some pull. That's why there's 200 newtons there. But, right, but it doesn't pull as much. So when you go to the moon, you lose weight, right? You lose weight. Okay, next one, we got length and volume. So length is how long an object is. Usually we use a ruler for that, or a meter stick. And again, whenever we do this, we're going to be working in centimeters or meters, not inches, right? And then volume is the amount of space an object occupies. Usually that's measured in liquids, but you yourself sitting in your room right now, right? You are taking up volume. You're taking up the volume of the room, and we'll talk about that some more later. We also measure temperature, how hot and cold something is, and then time, how long. So these two are a little bit more familiar with you guys. You know, we check the temperature every day, we check the time every couple minutes, right? But those are things that we will measure. Here's a table for you. I would suggest to write this down. These are the measurements we just talked about and the metric base units. So we got grams, right, for mass. Sometimes you'll see them, whoops, sorry. Sometimes you'll see them as kg, that's kilograms. Same thing with centimeters. Sometimes you see them cm, centimeters, or km, kilometers, right? Volume is measured in liters. That can be either milliliter, right? You might see it that way. Now, temperature, you know, the metric system is Kelvin, but that is not what people use. They usually use Celsius, right? So even for us, what we're gonna do, you guys, is we're gonna use Celsius. Most thermometers use Celsius, but there's a handy dandy little conversion to use to convert to Kelvin. But for right now, we'll use Celsius. And then time, usually we do in seconds. And depending on what we're measuring, we can be doing minutes or hours, even days or years, right? Just depending on what we're looking at. Okay, so here's the fun stuff. You don't need to worry about that. You can draw it if you'd like, or you can print it if you'd like, but I would have this handy until you get the hang of it, because it does help you in so many ways. Right? This is called the ladder method. This is what we will use in order to convert between different things. Now you might ask, well, why do we need to convert these things? Because sometimes you are given a specific type of measurement, but maybe you only have the tool to measure it this way and not that way. So you're gonna have to convert, right? Or maybe you're like me, right? And you were given the wrong measurements, and now you gotta convert it into the right measurements, right? So all of these, you guys, these are all prefixes. Prefixes means that they go in front of the word, and they go in front of, well, of these words. Sometimes this one. They go in front of those. That's where the kg comes from, the cm, the km, and the lm. All of these, the k, the c, the k, and the m, those are these, the kilo, hecto, deca. So that's why you can say kilogram, right, or milligram, or centigram, and so on. So we're going to use this as our ladder method. So something I want you guys to pay attention to is these two things right here. So if you want to convert to a larger unit, you move the decimal point to the left, or you divide. If you are converting to a smaller unit, you move the decimal point to the right or multiply. So up here, this is the bigger units and these are the smaller units. Right? So let us figure out how the steps. So 3 steps. First thing is you determine your starting point. So what were you given? What was the measurement given to you? You count the number of jumps to your ending point, and then you move the decimal the same number of jumps in the same direction. So let me demonstrate for you. Here's our example, right? For km means kilometers, and then m is meters. Right? And then you might be like, oh, well, I don't see meters on here. They're all lumped up right here on the basic unit, right? So first step is to figure out where we're starting. So we're starting in kilo, which is up here. That is our start. And we want to get to meters, which is right here, right? So what you're going to do is you're going to jump on the boxes and you're going to figure out how many jumps it takes to get there. And this one already did it for you. So we're going 1, 2, 3 jumps. Right? Now, this is important. Are you going to the left or to the right? Hopefully you said that you're going to the right, right? Because I started in kilo and now I'm going to meters. So here's 4. Let me rewrite it over here so that you can see it a lot bigger. 4. When you see a whole number with no decimal, the decimal is usually going to be at the end of the number. So that's why some people, they say 4.0, right? But 4 and 4.0 are the same thing. They are the same thing. So we're going to take that decimal and we're going to go to the right 3 times. So we go 1, 2, 3, and decimal ends up right there. And then you fill in your little brackets. So if you're converting 4 kilometers to meters, that's 4,000, right? Or you can say 1 kilometer is equal to 1,000 meters, and then you just convert from there. Right? So that's an example right there. But again, you got to know if you're going left or right, because that is the most common mistake that I've seen, that you're going the wrong way. And then, you can put the decimal right here, but we're going to talk about significant figures later on. Just for our sake right now, or if you're in biology, right? Biology, it sounds kind of weird, but you don't have to worry about significant figures too much. Chemistry, you do have to, because when you're working with chemicals and stuff like that, you need to be to the point of, being exact and accurate. Okay, so here's the acronym, right? On the quiz, remember, you can use your notebook. On the test, you cannot, right? And I will not give you this on the test, so you might want to remember this. So here's an acronym. King Henry died by drinking chocolate milk. Some of them say something else. I've heard it another way, but this is how I remember it. So King Henry died by drinking chocolate milk, right? So what this is the K represents the kilo, we got the hecto, we got the deca, we got the base units, we got the deci, we got the centi, and then we got the milli. So notice, you guys, that I wrote deca and deci differently. Deca with a capital D and deci with a small d. That's how you know they're different, because if I put decagrams, then that's capital D and then small g. If I said decigrams, then it's lowercase letters for both. Right? So just be mindful of that if I end up using abbreviations. Okay, so King Henry died by drinking chocolate milk. So every time you drink chocolate milk, right, or hot chocolate, since the holidays are just around the corner, think about King Henry and think about conversions. Okay, so here's a few more practice. So at this point, what I would say is I would suggest to pause the video, try it out first, and then play again, because I'm going to show you how to do it. Right? So pause the video right now, take a couple minutes, and try this on your own. Okay, hopefully you've tried it on your own, but if you're still confused and you just need to see it one more time, then here we go. So we're going from meters to centimeters, right? So first things first, you got to figure out where you're starting. So for this first one, we're starting here, and then we're going to centi, right? Hopefully you said that we're going to the right, and then you just got to figure out how many jumps to get from meters to centimeters. You start here, you go 1, 2, that's 2 jumps. Number 1 gave you guys a decimal point. So if they give you a decimal point, just use that. And again, we're going to the right 2 times. So we're going to take that decimal point and go 1, 2, and your decimal point is going to end up right here, right? So your answer should be 603 centimeters. Right? Let me see. Can I erase? Oh, yes, I can. All right, let's do number 2. 4,193 liters to milliliters. So liters, again, is right here on our basic units, and we're going to milli, which is over here, right? So there's our start, there's our finish, and we're going to the right. So we're going to jump and count the boxes. We go 1, 2, 3 jumps, right? And again, remember this one, they did not give you a decimal point, so the decimal point is right here on the end, the very, very end of the number, right? So we're going to move that decimal points 3 times to the right. We go 1, 2, 3, and that moves right there, and then you fill in your gaps, right? So we have 194193, 1, 2, 3, and then I just like to put the commas so I can read my place values correctly. So now we have 4,193,000 milliliters. Okay, and last one. Let's erase this one again. Okay, last one, we got 791,300 milligrams, right? So we're going from milli to grams, which is over here. So now we're going backwards. We're actually going to the left this time, but still the same number of jumps. We go 1, 2, 3, right? And again, this one does not give you a decimal point. I know there's a comma there, but we're looking for decimal. So your decimal point is going to be here at the end, and then we're going to the left this time, right? So we go 1, 2, 3, and it just so happens to land where that comma is. So our answer would be 791.3 grams. We don't need those zeros there anymore, right? 791.3 grams. And that's it. Oop, there are all the answers. Right, so now you're going to practice on your own. Right, I'm going to give you a worksheet, and then we'll go over those together, or if we run out of time, then I will give you the answers to the question at a later date. Right, if you need to watch the metrics one again, please do. It does take some practice and it does take some time. All right, you guys, I'll see you guys in the next video.